Welcome to my differential equations course. Today we'll be covering separable equations. What is a separable equation? A first order differential equation of the form dy over dx equals g as a function of x multiplied by h as a function of y, or m as a function of y dy dx plus n as a function of x equals 0 is said to be separable or to have separable variables. So how exactly do we solve a separable equation? Well, first we begin by separating the variables. Right here you can see that we move all our y variables to the left side and all our x variables to the right side. Then we integrate both sides, and upon integrating both sides we obtain the general solution of capital H of y equals capital G of x plus our constant. From here we solve for y if possible. So let us do some examples. So how do we solve this differential equation? Well, by the method of separation of variables, we begin by separating the variables. As you can see here, we move all our y variables to the left side and all our x variables to the right side. And then we integrate both sides. In this case, the integral of 1 over y equals the natural log of the absolute value of y, and the integral of 1 over 1 plus x dx equals the natural log of the absolute value of 1 plus x. And then we add our constant at the end. We take the exponent of both sides. Because we take the exponent of both sides, we don't actually change anything in our equation here. We don't change the equivalence. And I'm just going to note one thing here, an exponent law. When we take a to the power of n plus m, this is the same as a to the power of n multiplied by a to the power of m. Note a is the same base. So if we look at the right hand side of our equation here, e now becomes e to the power of natural log of the absolute value of 1 plus x multiplied by e to the power of our constant. If you look at the left hand side, we applied another property of exponents. E to the power of natural log simply cancels and we're left with the absolute value of y. Likewise, we're going to repeat the same thing on the right hand side. E to the power of natural log of the absolute value of 1 plus x is cancelled, and we're left with the absolute value of 1 plus x on the right hand side. Now, we can't leave our solution in this form. We can't leave our solution with the absolute value bars on them. So we get now y equals plus or minus e to the power of our constant multiplied by 1 plus x. We still can't leave our solution in this form, so we're going to relabel plus or minus e to the power of our constant by a, and we're left with our solution, y equals a multiplied by 1 plus x. Let us now solve another problem. So how do we solve this differential equation by separation of variables? Well, we start off the same way. We separate the variables. We move all our y variables to the left side, all our x variables to the right side, and then we integrate both sides. Now, the integration of 1 over y squared dy is just simply negative 1 over y, usually plus our constant. But the integration of the right hand side will require a little more creativity. So I just want to note one thing. E to the power of x divided by e to the power of x simply equals 1. So if we're to multiply the numerator and the denominator by e to the power of x, we're simply multiplying by 1 and we're not actually changing our integral. However, because we're doing this, we're able to get a little clever here and massage our integral into something we could work with. So by applying our exponent laws, we're left with the denominator equaling e to the power of x plus e to the power of negative x plus x, which simplifies the denominator to e to the power of 2x plus 1. Let us note one more thing here. E to the power of 0, because negative x plus x equals 0, e to the power of 0 simply equals 1. Anything to the power of 0 will equal 1. And we're going to note one more thing here. When we take the integral of u squared plus 1 du, this simply equals arctan of u. With this in mind, we now know the integral of 1 over e to the power of x plus e to the power of negative x equals arctan of e to the power of x. So now we solve the left hand side and the right hand side integrals. So then we're left with negative 1 over y equals our arctan e to the power of x plus our constant. Now we try to solve for y. Y simply equals negative 1 over arctan times e to the power of x plus our constant. And this is the solution to our differential equation using the method of separation of variables. Let us now solve this differential equation by separation of variables. We'll start off again by simply separating the variables. And if you can see here, we have all our y variables on the left side and all our x variables on the right side. We integrate both sides. And when we integrate the left-hand side, we're left with arc sine of y. When we integrate the right-hand side, we're left with 1 over 2 x squared plus our constant. Now, in this case, we can solve for y if we get a little bit clever. If we take the sine of both sides, the left-hand side would simply become y, and the right-hand side would become sine of 1 over 2 x squared plus our constant. And this is the solution to our differential equation. Now let's solve something a little more challenging. So to solve this differential equation, we will start off with separating the variables. Or at least we would start off with separating the variables. However, in this case, we need to actually simplify the right-hand side of our differential equation before we're able to separate the variables. So let's get a little clever here. Let's start off with factoring out y from the first two terms in the numerator. Upon doing so, we're left with the following. And then we factor out a negative 1 from the last two terms in the numerator. So we factor out a negative 1 from negative x minus 2. Upon doing so, we're left with the numerator you see. And then we do the same thing in the denominator. In the first two terms of the denominator, xy minus 3y, we have y's. So we factor out the y's from those two. And then in the last step, we factor our x plus 2 in the numerator. That's the common term. And we factor our x minus 3 from the denominator. And then we're left with the following. So now our original differential equation, which was dy over dx equals xy plus 2y minus x minus 2 over xy minus 3y plus x minus 3, simply becomes dy over dx equals x plus 2 multiplied by y minus 1 over x minus 3 multiplied by y plus 1. Now we continue to separate the variables. Upon separating the variables, moving all our x variables to the left-hand side and all our y variables to the right-hand side, we get the following. Now we got to integrate both sides. Now let's start off with integrating the left-hand side first. I want to note one thing. Negative 3 plus 5 equals 2. So when we take the numerator here, x plus 2, and we change it to x minus 3 plus 5, we simply transform our numerator, but we actually have not changed our numerator at all. But upon getting a little clever here and transforming our numerator, we're able to solve this integral quite easily. So now we get the integral of x minus 3 over x minus 3 plus 5 over x minus 3 dx. This simplifies to the integral of 1 plus 5 over x minus 3 dx. Now the integral of 1 is simply going to be x. The integral of 5 over x minus 3 is simply going to be 5 times the natural log of the absolute value of x minus 3. And now we have solved the integral for the left-hand side. But now we have to integrate the right-hand side, the integral of y plus 1 over y minus 1. Similarly to the last integral, we take a look at our numerator, y plus 1. What we decided to do here was decided to subtract 1 and add 1. We effectively just added 0 to the equation. However, we could massage this problem into something that we could work with. We're left with the integral of y minus 1 over y minus 1 plus 1 plus 1 over y minus 1 dy. And now you might be seeing where I'm going to be going with this here. Now we get the integral of 1 plus 2 over y minus 1 dy. And that is simply y plus 2 times the natural log of the absolute value of y minus 1. So we integrated both the left-hand side and the right-hand side, and we're left with x plus 5 times natural log of absolute value of x minus 3 equals y plus 2 times the natural log of the absolute value of y minus 1 plus our constant. We simply leave our solution in this form because in the natural log we have a y variable and we also have a y variable outside of the natural log. So we simply leave our solution like this. Now, we're going to solve initial value problems. So what is an initial value problem? So on some interval I containing x naught, the problem, this differential equation, subject to these constraints, is called an initial value problem. Let's just note that 1 is called an nth order initial value problem. So we're only going to learn how to solve these type of problems, initial value problems, by doing examples. So let us do just that. So how exactly do we find an implicit solution of 1 plus x to the power of 4 dy plus x multiplied by 1 plus 4y squared dx equals 0, subject to the initial conditions of y of 1 equals 0? Well, first, we just simply solve the differential equation and we disregard the initial value. So we're going to do this by separation of variables. We're going to remove all our y variables to the left hand side, all our x variables to the right hand side, and now we're going to integrate. Okay, I just want to note something here. In exponent law, a to the power of n to the power of m is simply a to the power of n multiplied by m. So you see here that in the denominator of my first integral of 1 over 1 plus 4y squared dy, my 4y squared, I transformed that to 2y all squared. Remember, that is still the same as 4y squared, but we did this integral in this way to simplify our integral, because we're going to transform it to make it look like the integral of 1 over u squared plus 1. Likewise with the integral of x over 1 plus x to the power of 4. Exactly the same thing. So let's integrate the left hand side. Let's dive in a little deeper so we can understand what exactly we're doing here. If I use u substitution, I say u equals to 2y, du equals to 2 dy, I'm able to transform my integral to the following: 1 over 2 integral of 1 over u squared plus 1 du. We already know what this integral is. It's arctan of u plus our constant. So now if we substitute our u for 2y, we get 1 over 2 arctan 2y plus our constant. Now let's integrate the right hand side. Negative integral x over 1 plus x squared squared. Again, we use a u substitution here to simply show you exactly what we're doing here. So u equals x squared, du equals 2x dx. Upon doing this, we get negative 1 over 2 integral 1 over u squared plus 1 du. We already solved this problem. This is simply arctan of u. So negative 1 over 2 arctan of u plus our constant. So when we substitute back our u for x squared, we get negative 1 over 2 arctan x squared plus our constant. So we solved the left hand side and we solved the right hand side. We solved both integrals. So now the solution to our differential equation is 1 over 2 arctan 2y equals negative 1 over 2 arctan x squared plus our constant. Now this is the solution to our differential equation, but not the solution to our initial value problem. So the constant, we need to find out what does the constant equals. So we're going to apply the initial conditions. Y of 1 equals 0 to solve for our constant. So let us note here that x equals 1 and y equals 0. So 1 over 2 arctan of 2 times 0 equals negative 1 over 2 arctan 1 squared plus our constant. Arctan of 0 is 0. Arctan of 1 is pi over 4. So therefore our constant equals pi over 4, and the implicit solution to our initial value problem is as follows. See, not so bad. So now let us solve this problem. How do we find an implicit solution of square root of 1 minus y squared dx minus the square root of 1 minus x squared dy equals 0, subject to the initial condition of y equals 0 equals square root 3 over 2. Well, we solved the differential equation just like before. We separate the variables, remove all our x variables to the left hand side, all our y variables to the right hand side, and we integrate both sides. Now, the integral of 1 over square root 1 minus x squared dx simply equals arc sine of x. So we have the solution to our differential equation here. Now we apply the initial conditions. Y of 0 equals square root 3 over 2. Now let's note x equals 0 and y equals square root 3 over 2 when we do our substitution. So we get the following. Arc sine of 0 equals 0. Arc sine of square root 3 over 2 equals negative pi over 3 plus our constant. Now c equals pi over 3. And the implicit solution to our initial value problem is arc sine of x equals arc sine of y plus